On number one, it says compare how rays and wave fronts are similar and how are they different. So what are they in the first place? Well, wave fronts are going to show you the crests of either the electric field or magnetic field. And so say we had something here that was producing light like a candle. You could draw wave fronts coming off of it, and they would be small at first and then bigger and bigger and bigger, and it just shows how the wave is spreading out as it goes. So those are wave fronts. If I wanted to draw a light ray on that, rather than drawing those wave fronts, I would just kind of draw the direction of it. And so it would just be a straight line like this. You can see how much easier that is to draw, and so that's why that's drawn so much more often. So they both show how light is traveling, and so that is how they are similar. They are different in that the one shows how light spreads out and the other one really doesn't show that very well. And the one shows the wave crests, whereas the other one doesn't really show that, it just shows the direction. Number two has a picture, and it says a beam of light reflects from a mirror as shown. It says if the angle of incidence of the beam is increased, does the reflected beam shift towards number one or towards number two, or does it just stay where it is? Now this is an easy one, but we got to know what they're talking about to get this right. The angle of incidence is this angle right here. You know that's the angle of incidence because it's between the incident light ray, that is the incoming light ray, and the normal line. The normal line is that line that's going to be perpendicular to this interface. The interface is this surface of the mirror right here. Don't be confusing the incident light ray and the interface. The incident light ray is a ray of light. Interface is that place where the air stops and the mirror begins. Okay, so now that angle is between the normal line and the incident light. And the angle and the law of reflection says that that angle of incidence and the angle of reflection are always going to be the same. Where's the angle of reflection? It's this one right here. It's between the reflected light and the normal. So it's this one right here. Those two are going to be the same. So now if they're saying the angle of incidence is going to increase, well, that would say that it's now, instead of the incident light ray coming in along that line, maybe it's coming in more like this. See, there's a bigger angle of incidence. And so what's that going to do to this reflected ray? Well, it's going to have a bigger angle of reflection too, and so it's going to move more towards this. So it's going to be more towards number two. Number three says, which type of surface, a smooth one or a rough one, produces clear reflected images? Well, it's going to be the smooth one, and here's the reason. It's the smooth one because whenever the surface is smooth, the incident light rays coming in, maybe they're parallel to each other, they're going to reflect and they're going to stay parallel to each other, you see? And so whenever you're standing over here looking at this, they're going to get into your eye in the same orientation as they started off with. They're not going to get all jumbled up. Versus if the surface is rough, even if it's a little rough, the incident light rays are going to come in maybe parallel like that, and now there's a little bit different looking normal on each one of these. And so, I don't like it last normal, a little bit different looking normal on each one of those. And so that means that you're going to get light rays, they're going to be traveling all over the place, and I'm not saying that they're not going to get into your eye, but they're certainly going to get all jumbled up. And so whereas this person up here is going to see a clear image, this person down here is just going to see light, and it's not going to look like a clear image. Number four shows a picture, and it says that the picture shows a horizontal incident beam of light, that's this one right here, reflecting from a mirror inclined at an angle theta from the horizontal. The reflected beam of light makes an angle phi with the horizontal. So I want you to think of this horizontal line coming all the way across, and whenever that reflected beam crosses it, what kind of angle does it do? Is it making an angle like this? They want to know if you increase this theta, is the angle phi, is it going to be even steeper or is it going to be less steep? Well, if you think about it as a static situation, you might actually struggle with this one. But if you think about it as just that horizontal line coming all the way across, you might be in good shape. So that's theta right there. Now, if we made theta bigger, that would mean that mirror would be inclined more like this. What else changes? Pretty much everything. The normal now is going to go like that. And so now look at what happens with the light ray. The light ray is going to it's going to come in like this now, and now it has to make the same angle with the normal. Actually, I should have drawn that normal more like down in here, but nonetheless, it's going to come out here like that. And so see, the angle with the horizontal is this one. That is, it's going out real steep. And so when you make theta increase, then that makes phi increase too, because of the angle of reflection. The angle of incidence right there, angle of reflection right there, have to be the same thing. And so if you make the mirror steeper, well then the reflected ray is going to be steeper too. Number 5 is a takeoff on that last one, the same picture. It says if the angle of the mirror relative to the horizontal is 30 degrees, then what's the angle of incidence? Well, the angle of incidence is going to be this one right here. Now look, this was a horizontal light ray coming in. And this dotted line down here is horizontal. So alternate interior angles say that this angle in here is 30 degrees. Now, the angle of incidence right there is the complement to that. And so that's going to be 90 minus 30 or 60 degrees. Number 6 uses that same picture, and it says, suppose that the angle theta is 20 degrees. What is the phi angle? Now, I actually think this one's kind of a tough one, and the geometry is a little bit strange. So follow me on this, please. So what I did is I drew this construction line right down here like this, perpendicular to that horizontal line. Now, I can show you that if this angle's theta right here, then this angle's going to be theta up in there too. Now think about this for a second. If the mirror were lying flat, just like that, no good. Mirror's lying flat, more like that. Okay, and then here's that black line that I just drew. Okay, straight up. Now, if I took that angle, that mirror, and I inclined it 1, 2 degrees, maybe it's there, maybe 5 degrees, maybe it's like that. Okay, and so this angle right here is that angle theta. Now, what happens to that normal line? Well, that normal line, that black line, well, now it gets turned by theta as well. Okay, and so however many degrees I picked up the mirror, that's how far the normal line went too. So I'm trying to show that if that's theta down in there, then this is theta up in here too. Let me put a little bit nicer theta on there. Okay, so now if you buy that part, and I hope you do, then that's theta, and so this angle right here is theta as well because of alternate interior angles. So they told me something. They told me that this theta was 20, so I know that there's 20 in there. Now, this angle of incidence is a complement to the 20, and so that's going to be 70. And so angle of incidence, angle of reflection, same. Now the angle of reflection is going to be that one, and so there's 70. Now look at this. I said theta was 20 down here, and I tried to show earlier that that angle's the same as theta, so that part's 20. So that means that this part in here is 50. Okay. Now, if I want you to look at this triangle right here, and I'm going to draw that over here again, 90 right there, 50 down there. Yes, I know I drew it way up in there, but really it should be down in that point. And so that makes this 40. Now, so there's 40 there. That means it's 40 right there. And theta, or phi rather, is the same size as that 40. And so I'm saying that that's 40 degrees. A little bit tougher one. Number 43 says a beam of light strikes a mirror at an angle of 23 degrees to the normal. What's the angle between the incident and reflected beams? Some people are going to make a mistake here and they're just going to jump to 23 because they know incidence and reflection are the same size, but I don't want you to make that mistake. So let's say there's our normal, and let's say this is the mirror. And so if I wanted an angle of incidence of 23 degrees, that's going to be something like that, 23 degrees. It's going to reflect so that we have 23 degrees right there. Let's see something. They're not asking for that 23. They're asking for the angle between the incident and the reflected beams. So they're going for this whole 46 degree angle. On number 44, it says a ray of light reflects from a plane mirror with an angle of incidence of 37 degrees. So maybe something like that, 37 degrees. What's the angle between the plane of the mirror and the reflected beam? So they're not actually asking for an angle that we have a name for. They're asking for this angle right here. This is going to be 90 minus 37, 53 degrees. Number 45 is a neat one. It is two parallel mirrors, and it says how many times will the light reflect back and forth from the top and bottom mirror. So you can see what's going to happen here. The light is going to come up here, just barely miss this bottom mirror's edge, and it's going to reflect and it's going to come back and it's going to keep bouncing back and forth, back and forth. Here's what I thought about. I thought about normal line right here. Now they're saying that that's 15 degrees up there, but if I can push this down in here a little bit more, there's where that 15 degrees is. And so this is also 15 degrees. We know that that solid black line that they drew and this yellow line that I drew are parallel, and so there's 15 degrees right there. Now I want you to focus on that triangle right there, the one that's yellow and black, like this. Now that's a right angle right there, and this is 15 degrees up here. Now we know that this yellow side is 68 centimeters long, so it's not hard to use a little trig to see how long this X is. Can you think about how to do that? I would say that it was tangent to 15 degrees is opposite over adjacent X over 68 centimeters. Now if you do that, if you go X is equal to 68 centimeters tan 15, you're going to get X is 18.22 centimeters. Okay, so now you see X in the picture. The X is this short side of the triangle right there. There's an X, and there's an X, and there's another X, and there's another X, you see? And there's an X up here, and two of them right there. And so all these triangles that I'm making are all exactly the same size, are all mirror images of each other. And so how many of those 18s are going to fit along 168 centimeters? Well, I'll go 168 centimeters divided by 18.22 centimeters, and I'll get 9 of them, 9.22 of them. So that means this light is going to reflect so that there's 5 of them at the top, and 7 of them at the top, and 9 of them at the top. Now 9's not the answer. They said how many times does it reflect? It reflects 1, 2, 3, 4, 5 times, because that's how many of those little triangles can fit across there. But remembering you have to double them up. So it reflects off the top 5 times. Now what about the bottom? Well, I got an X and an X and an X, and as you can see here, if I did this, I will get 1, 2, 3, 4 times reflecting off the bottom, and it's coming down towards the bottom, but it's going to run on a mirror. So it's only 4 times reflecting off the bottom. You might say, how do I know that it's not going to hit the bottom? Well, if you counted these X's, I got 10 of them across there, and it's run out of room. This is not going. On number 46, it says you're standing in front of a very small mirror. You're 2 meters from that small mirror, and you see the reflection of your belt buckle, which is 0.7 meters below your eyes. What's the vertical location of the mirror relative to the level of your eyes? So let's draw a picture of this thing. Here you are. Here you are. Here's your belt buckle right there. Okay, and here's the little mirror. Now, you say, well, how do I know where to draw that mirror? Listen, I know that the angle of incidence and the angle of reflection have to be the same. So if the mirror is right in front of your eyes, when that belt buckle image hits it, it's never going to hit your eyes. But if it's down lower, then it has a chance to hit your eyes. There. Okay? So you see it. Now look at this. I'm thinking about drawing the normal on there. And so here's the angle of reflection, here's the angle of incidence, and those two things are going to be the same. Now, they told us that this distance right here is 0.7 meters, and those two triangles are congruent to each other. They share that same angle, or that same side in the middle. The angles are the same. They share these 90-degree angles right here. So they are congruent. So all that is to say that this side on the top one and this side on the bottom one are the same size, so that means they're each half of the 0.7, so that means that the mirror is 0.35 meters below your eyeballs. Okay, now it says, what angle do your eyes make with the horizontal when you look at the buckle? So you have to look at the buckle, you have to look down a little bit. Here's horizontal for your eyes, and they're asking for this angle right here. It happens to be the same size as that angle of reflection. So let me draw the triangle over a little bit. So there it is. This side is 0.35. It said you were 2 meters from the mirror. How big is that angle right there? It happens to be the same size as this angle, which is the answer. So that angle is going to be an inverse tan of the opposite over the adjacent, both in meters. When you go ahead and do that, you get 9.926 degrees, just two significant figures there. Now it says on C, now if you move backward until you're 6 meters from the mirror, will you still see the buckle, or will you see some other part of your outfit? Well, let's see here. So let's say we move you back. Let's say we move you back. That's 2 meters. I'll move you back to here. Let me try my best to draw you the same size. Okay, and so now there's something from the mirror to your eyes, that line is going to look something like that. You almost missed the mirror. And the normal, there's the normal way back there, and that angle is real small this time. Okay, but here's the thing. The angle of incidence and the angle of reflection still have to match each other. And so my picture doesn't look very good. Some of my lines aren't real straight, but I will say this. This distance right here from your eyeballs to the normal, and this distance from the normal to whatever you're seeing, well, they're the same size as each other. And so as long as where your eye is above the floor and where the mirror above the floor haven't changed, that's still that 0.35 meters. So you're going to see something that's 0.35 meters below that. So what's there? The belt buckle. So you can go as far back from this as you want, and as long as your eyes don't change height and the mirror doesn't change height, then you're going to see that belt buckle. So if you want to see something else, you're going to have to crouch down or stand on your tiptoes or something like that. Still see the belt buckle. On number 47, there's light coming in from a window, and it hits a mirror that's laying flat on the floor, and maybe it's a little reflection of the sun. There's a spot of light that is created on the wall right there. And then you're going to take a pencil and you're going to stick it underneath the one edge of the mirror, and that's going to incline the mirror up a little bit, and that's going to make the light reflect up a little bit higher, and now the image of the sun is going to be right there. And they want to know how much higher up are you making the light reflect. Pretty good problem. So let's look at it in the first place. In the first place, I got 32 degrees right there, and here's my normal. And so this is 58 degrees, and this is 50. Don't look at that light blue one there. This is 58 degrees, all of that. And so I have 32 degrees right there. Now, look at that triangle, this one here, here, here. I have a 32-degree angle down here on the left. I have 2 meters on this adjacent side. And so then how big is this y? Well, y is going to be 2 tan 32. And if you go ahead and do that, you get 1.25 meters. Okay, so then you put the pencil under. And with the pencil underneath there, now the angle becomes 5 degrees underneath there. So the new normal line, instead of going straight up, it's going to be tilted from what we used to have by 5 degrees. Okay, so now if I have 32 degrees here, these two angles no longer add up to 90, they only add up to 85. And so instead of this being 58, now this is going to be 53 degrees. Okay, so angle of incidence is 53 degrees. And so angle of reflection, do you see it right here? It goes from the normal, not the old normal, the normal, over to the outgoing light. And so there's 53 degrees right there. So this little part right in here, that's from the old normal down to the reflected light. That's 5 degrees less. And so this part is 48 degrees. And I make an issue of that because the old normal is perpendicular to the floor. And so now 48 degrees, and then this is the complement to 48 degrees, so that's going to be 42 degrees. So now I have the same thing as I had before. I got this spot up here, and it's a triangle that it's still 2 meters from the wall, but it's taller now. And so how tall is it? Well, that y is going to be 2 tan 42 degrees, and this time that's going to give you 1.8 meters. So it used to be hitting up there at 1.25 meters. Now it's hitting at 1.8 meters, and so you can see that the difference between the two, 1.8 minus 1.25, is going to be 0.55 meters difference.